We are José Luis Muñoz and Ignasi Ramos. We both work at Polygon. We are at the zkEVM product, at the zkEVM department. I'm a software developer at the protocol team, and he's handling the documentation department. José is also an associate professor of the UPC, the Universitat Politècnica de Catalunya, and he's also the director of the master degree of blockchain technologies, which I strongly recommend. Actually, he was my professor in both, in telecommunications engineering and also in this master. So I'm very glad to be here doing a talk with him. What we are going to talk about today is about the zkEVM. The title of the presentation is called Demistifying a zkEVM. We will explain from the very beginning since why L2s and zkEVM appeared, the different type of zkEVMs, the different approaches technical approaches that has been taken depending on the different challenges that we've been facing, we and all the companies that are building L2s, and depending on the decision, on these technical decisions, different kind of L2s have been appearing. After that, we will talk more deeply about our product, which is the zkEVM at Polygon. And in more concrete, we will go very deep in one of the most important and most valuable components in our system, which is the prover. This second part of the prover will be a bit more technical, but the first one, it will be more, I think, more understandable and light. So let's start. Yes, from the very beginning, talking about Ethereum. Oh, no. As you can see, this schema, it's very easy to understand. We can see how most of the blockchains work and obviously how Ethereum's work. Everything starts with an state. An state completely defines a moment in the blockchain. It completely defines all the storage, all the values, all the different balances, nonce, bytecodes, storages of an account. And how a blockchain progresses. A blockchain progresses moving from one state to another. This is what we call state transition. I really like you to understand this state transition concept because I'm going to use it all along the talk. To move from one state to another, we get one initial state, for example, S sub 0. We get a bunch of transactions, which is called a block. We execute these transactions at the top of this initial state, and we get this new state. And we keep doing this, and this is how most of the blockchains works. And now we will go a bit deeper on how is from the inside a state. Thank you. The state from inside is an Ethereum. It's using a Merkle tree with a Keccak hash. In each one of the leaves of the Merkle tree, we have the values of each one of the accounts. We have the balance, the nonce, the bytecode, the storage of each one of the accounts. So it's very important to understand that this Merkle tree completely defines the state. How do we go up in a Merkle tree? Hashing two of the leaves in groups of two, we do a Keccak hash when we get a node, and we hash also with a Keccak this new node with its sibling. This way we go up and up and up 32 levels until we reach the top. The top is what is called the root. It's nothing else than a 32 bytes number that it completely defines the state. It completely defines the state of the blockchain in a moment. If I change just one bit of some of the values of the Merkle tree, the root will completely change. So what we are doing when we do a state transition is that we are moving from one root to a new root, applying a set of transactions. Once we understand a little bit the taxonomy of Ethereum from inside, let's talk about what happened years ago with Ethereum, what motivates us and other companies to do an L2. Many years ago, Vitalik, he did a blog post, it became very famous, where he first time uses the concept of blockchain trilemma. In this blog post, he defined 3 properties that a high-performance blockchain should have. We're talking about decentralization, security, and scalability. What he was referring on this blog is that with the technology and the math that we had on that moment, it was not possible on that moment, I insist, to do a blockchain that had these three properties in a balanced way. That this will be like the perfect blockchain. For example, if we make a blockchain with a lot of decentralization and a lot of security, we will be having a lag on scalability. This is the example of Ethereum, for example. But if we do a blockchain with a lot of security and a lot of scalability, we will be having a lag on decentralization. For example, the POS, the Proof of Stake network of Polygon. So, on that moment, a lot of different companies and projects started to try to create a solution. And the solution, the one that most prevails, are the L2s. And the solution, what they try to do is to extract all the logic of execution and computation of transactions outside of Ethereum, while they'll keep the decentralization and the security of Ethereum to consolidate the data availability. I will go more deep on this sentence during the talk. I know that maybe at the beginning can be difficult to understand. So I will repeat it. With L2s, we extract the computation from Ethereum. This is like the main objective, to get scalability while we keep the security and the decentralization. Now let's talk about L2s. As you can see, this schema is how an L2 works. It's exactly, well, very similar to the one we have just seen now of Ethereum. We have a state and we progress this to a new state processing transactions. But in this case are L2 transactions. So we are talking of a different blockchain, a different layer. I would like to progress with the talk about to explain the different type of L2s and how they have been evolving, answering the following questions. I'm going to read them. How users send L2 transactions and who receives them? How these L2 transactions are made publicly, meaning that what we do with the data availability, how to process the L2 transactions and how, and finally, what type of applications this L2 that we are doing supports. Let's start with the first one. The first one, it's very simple. It's how users send L2 transactions and who receive them. We have three different approaches. The first one is unicast. It's the most easy to understand, as the users, throughout an RPC call most of the time, they send the transactions to one centralized entity that processes these transactions. The second one, this one of unicast is the one chosen by most of the L2s, for example, by Polygon. The second one is a peer-to-peer. The user, instead of sending the transaction to one entity, he's sending it to a broadcast network. For example, an RPC network with a lot of different nodes who process, all of them, they process the same transaction and they reach a consensus to decide which one will be the result. This is the example, for example, of Ethereum. And finally, is through a smart contract. You send the L2 transactions to a smart contract that is deployed on L1. And then there's another entity that reads that transaction and executes them. This one is the more decentralized one, but also it's very cost. Let's go to the second question, which is, how are L2 transactions made publicly available? This means what we do with the data availability. This one is very interesting because it will create two different types of solution. From one hand, we have the rollups, which decided to do the data to consolidate the data availability on Ethereum. It consolidates the data availability on an L1. So this way, this data is decentralized and secure. On the other hand, we have Validiums. Validiums, what they do is that they store all this data in a data center or in a database in a centralized way. They are two different approaches, and both of them are considered L2s. Let's go a bit deep in each one of them. About rollups, it's what I've just said. They have a bunch of transactions and they consolidate it on L1. This is why they are called rollups, because they are rolling up a group of L2 transactions to one L1 transaction. It disappeared. Well, the problem of this it has some advantages, which it means that we are very decentralized and we are very secure, as Ethereum is giving us these features. But the disadvantage is that this is very expensive. Actually, the 90% of the cost of a rollup transaction is consolidating the data on Ethereum. Regarding Validiums, which is this slide, we are storing this transaction, this raw data, in a database, centralized, but we create what is called a cryptographic summary, for example, a hash of all this data, and this is this hash, which is small bytes, that are stored in Ethereum, just to prove that you are storing something that you had in the database. But this is not as decentralized as the other approach, but it's very, very, very cheap in comparison with a rollup. As you can see, when we are trying to make an L2 and we have to face the different decisions, we are also facing this blockchain trilemma that Vitalik told about blockchains. Now let's go to the next one. Yes, thank you. Who processes the L2 transactions and how, and when it is publicly considered that a new state is correctly computed. Okay, we are talking about which entity is executing these transactions, is processing them, it's deciding from this state and these transactions which one is the new state, and after this decision, when we consider this decision final, like it's not going to change, never. For this, we have three different approaches. From one hand, we have centralized execution. Let's see centralized execution.
Yes, the other way.
Okay, centralized execution, it's like very trivial. We send the transaction to a monolithic system. He processes the transactions, he decides which is the new state, and it consolidates the state on layer 2. You give the response of the new state in seconds, and you trust him. The problem is that this is not a trustless system. I mean, you are a user, trusts that this operator is behaving correctly. It's deciding the correct new state. But in case he's doing something wrong or he's creating a malicious state, you don't have any way to dispute his computation. That's why, well, this is a very centralized approach that it's have not been very adopted by most of the most important L2s in the ecosystem. So how can we create a system that allows the user to dispute the execution? This is solved by optimistic execution. No, no estaba.
No.
This is the case of optimistic executions. Optimistic executions, they have like two steps. The first one is like the one we have just seen now, a centralized execution. The user sends the transaction to this server that it computes a new state following his constraints, but with the difference that after proposing, and I say proposing, which means that it's not final, this state, it opens a time period, a time lapse of sometimes it's 3 days, sometimes it's a week, depending on the approach of the product, where users can submit a fraud proof to prove that this optimistic executor has done a malicious execution. In case this fraud proof indeed is proved, the optimistic executor that made this malicious execution is slashed, his staking is lost, and the state checker, that is the one who made the fraud proof, is rewarded. So with this solution, we really are getting more decentralization, and we really are processing the transactions as a rollup. But there is a problem, and it's the time between the computation is done and the result of the computation is final. Because me as a user, when I send a transaction and I get a result, I am not sure that this result is final until the time for a state checker to propose a fraud proof has passed. So we are saying that our transaction, our batch, our computation only will be final once this week period or this 3 days period or whatever has finished. So we really need a new approach to get fast and trustless final execution. This is the case of the next approach that we will see now, which is, wait. It's not. Well, it's succinct execution. Zero knowledge execution, yeah. But it's not appearing in the slide.
It's not appearing.
I mean, it's here, but it's. This is optimistic. Yes.
It didn't change.
No. I mean, it's changing in the computer, but not in the screen. Technical issues.
No, let me give it a try. Now it changed. It takes some time.
So we're validating the proof. Give us a minute. Our document is kind of heavy.
Not that we were going to the good approach.
It should change. But
Yeah. Okay, it's thinking. We got it. Yes. In the succinct execution verification model, instead of an optimistic executor, we have an execution prover. Instead of an executor, we have two components. We have a prover and a verifier. The prover, as the executor of optimistic, it computes a new state, but it also computes another thing. It computes a proof. It's a zk proof that mathematically, with zero knowledge, proves that this state transition is done correctly, following some constraints that we defined in the past. So there is no possible to dispute, since the zk proof proves the state is correctly computed. And the verifier is moved on L1. The verifier is handled by a smart contract. This is the approach that we are doing in Polygon zkEVM. So we are going to go deeper on this approach. And well, after we will talk more about it. As I've said, it has two components. It has the prover and the verifier. On one hand, the prover, it uses a lot of resources, a lot of CPU, a lot of RAM, and also it may take some time. I'm talking about minutes, 1 minute, 2 minutes. Also, it depends on the complexity of the state transition that is making the proof. At the beginning, the prover was a bit the bottleneck, but with parallelization of provers, this is no longer happening. And on the other hand, we have the verifier. The verifier is a code that is posted in L1, and it's succinct. It's very fast to prove. The proving time of a proof, it's constant. So it's like very light in comparison with the prover. So this one will be, in my opinion, the best approach to do an L1, and it's the one that we are following in Polygon zkEVM. Now let's go to the next question. This is not a question, it's a summary. Let's do a small recap on what we've been seeing. Depending on if the data is on-chain or off-chain, we have zk rollups and optimistic rollups, and if the data is off-chain, we have validiums and plasma. And depending on if we prove the computation with a validity proof, we have zk rollups and validium, and with a fraud proof, we have optimistic rollups and plasma. This web page is very interesting because it has like a rank of all the different L2s that are in the market. Yes, I would like to. Yes, that's nice. Well, here this graph is the total value locked of all the L2s. And yes, if you scroll a bit down, we have here a list of all the companies that have a product that is considered an L2 on mainnet and on production. And we have here different details in case we want to deploy our product or whatever in an L2. It's a very interesting web page to see which of these products best fits our approach. As you can see, they are sorted by total value locked, and the 5, 6 first one are optimistic rollups. They really are getting a lot of attraction for the users. They are actually, in this moment, cheaper than zk rollups and also faster. So I'll strongly recommend you to visit this webpage. And now, yes, that we have the next question is applications, yes. I think this is the last question to classify all the types of L2s, and if we are doing an L2 with a simple or a rich processing. What is a simple processing? As the name says, simple processing is very simple. It means we are doing an L2 that only supports transferring balance or tokens. The first rollups only support this kind of logic. It's very simple because in the Merkle tree I only have to storage the balance and the nonce of the accounts and the state transition. It's very simple. Actually, most of these solutions are deprecated, and all the companies have been moving to the rich processing. The rich processing, of course, can do the same as the simple processing, but it also can execute code, like Ethereum. There is a common approach of all the L2s, which is to be as compatible and as equivalent as the EVM, the Ethereum virtual machine. And of course, this means rich processing, because the EVM can process code and, well, a lot of stuff, and not only transactions. And now we will see a classification that Vitalik did years ago to classify the current L2s in the market, how compatible or how equivalent they are with the EVM. And he did this chart. 1 means equivalence or very compatible, and 4 means less compatibility. And as you can see, this has changed a lot. But years ago, it was like this. As most performance means that we are less compatible with the EVM. The types goes from 1 to 4. 1 means that it is exactly this L2 that you are doing is exactly as Ethereum. It behaves exactly the same. And when I say exactly the same, what I mean, do you remember when I talk about the Merkle tree, the state root? What I mean, if I have a state in Ethereum and a state in the rollup, and I apply one transaction, I will get the same root. The state result will be the same root on Ethereum and on this rollup. Currently, there is no product, as far as I know, that has reached this challenge to make a type 1 zkEVM on mainnet. But I know that there are different companies that are trying it. Actually, there is one department in Polygon, I think it's Polygon 0, that they are trying to do it. Type 2, it's the difference with the EVM, is that the state transition is the same, but internally, the tree, it's a bit different. For example, as I said before, on Ethereum, we use a Merkle tree. And the hash that we use to create this Merkle tree are kechunks. For the Polygon zkEVM, that we are a type 2 zkEVM, we use a sparse Merkle tree. And the hash function for this tree, it's Poseidon. This is a technical decision that was done because Poseidon is more friendly to compute proofs and to use with zero knowledge in comparison with kechunk. This type 2.5, which is at the middle, it's like type 2, but there are some gas changes. For example, calling some opcodes consumes more gas in the L2 than in Ethereum. Regarding type 3, in type 3 we start to find some incompatibilities, for example, a lack of some precompilates. And finally, type 4, in my opinion, type 4 it's almost not an EVM, but what they are doing is that, well, there are a few incompatibilities, and also that they are not like compiling in low level the EVM, but they are applying zero knowledge, applying proofs to the compilation of Solidity. So this will be like the classification. And this now, yes, that is the last question. This is additional question, is, are we scaling with zk rollups? The answer is yes, because the smart contract execution resources for verifying a proof are much lower than executing individual transactions within a batch. This is true, but this also can be seen if you see the price of doing a transaction in a rollup in comparison with doing a transaction on Ethereum. I don't know, it varies a lot, especially on Ethereum, but I don't know if in Ethereum it's like 30, 25 cents. In a rollup, it's 10 cents. And this will improve a lot. Well, actually, in optimistic rollups, it's 1 cent or less. But in zk rollups, this will improve a lot in the following months when we will deploy a new hard fork that supports the new EIP 4844 done by the Ethereum Foundation, which supports blocks, making that posting the data availability on Ethereum by a rollup, it's far, far, far more cheaper than now. After applying this hard fork, probably the price of doing a transaction in a zk rollup will be around 2 cents. So this is a summary of all the questions, but answered thinking on the Polygon zkEVM. As I have said, we use unicast for the users sending the L2 transactions. We consider our product a rollup because we are consolidating the data availability on Ethereum. And we are a zk rollup because we are using a zk executor. And finally, we are an EVM, so because we are a type 2, because the same process and the same logic that can our rollup do, it's the same as Ethereum, as an EVM. So that's a little bit of the history of how an L2 has been evolving. Now, Now we will focus more on our solution, which is the Polygon zkEVM. Now that you have like all this context, you know a little bit how does it work, which are like the competitors or the other companies that has done different approaches. This is the different components that make the zkEVM at Polygon work. Now we're going to explain a little bit the flow and some of these components, and then we will focus on the prover. Jose will explain the prover deeply and in detail, which is very interesting. Actually, I would say that it's the most important component of the infrastructure. It's like the differentiation with other companies. ¿Vas a explicar el flow?
¿Vas a explicar el flow o no?
Vols utilitzar d'introducció tu mateix?
Bueno.
Sí? Bueno, sí. Does anybody has any question? Or?
Oh yeah, let's do a
Sorry.
small...
I'm going to pass the microphone to Jose, but before, sorry to ask, do you have any question regarding what we have just explained? Yes.
I don't understand how you migrate from Polygon proof of stake to Polygon zkEVM, and what consequence has this in the user. I mean, he uses the MetaMask and changes in 2 different networks. He pays the gas fees with Matic, or the pays with the L2 Ethereum in the zkEVM?
Okay, this is a very good question, and I understand why you are doing it. Everybody, when thinks about Polygon, they think about the POS because it's the most famous chain. Actually, it has a lot of traffic and millions of active accounts and users. But the zkEVM, it's a different chain. They are not related. A transaction that is done in the POS, it's not happening in Ethereum. In the zkEVM of Polygon. So they are different. And regarding your second question, the POS is still using Matic, but the native token of the zkEVM is Ethereum. So are different, completely different products. Yes.
And the zkEVM basically settles not to Polygon POS, but settles to Ethereum, right?
Exactly, yes. The zkEVM settles to Ethereum, not Polygon. Actually, Polygon POS, it's not a very decentralized approach. So we prefer to consolidate, obviously, on Ethereum. This way we get the security and the decentralization of Ethereum. Also, I would like to add something. Maybe in the future, the POS, yes, that will transact not to a zkEVM rollup, but to a zk Validium. This may will happen in the future with the plans of Polygon to do this whole thing of the aggregation layer and the Polygon 2.0. Yes, another question.
So with zero knowledge, you can virtually prove execution of any code. Why do you think that everyone is so focused on EVM when the EVM has some scalability issues itself? Like we could be fighting for more computationally efficient VMs.
Making zk proof of the EVM, I don't think it's easy. I mean, it's very complex and it requires a lot of computation, actually. If you want to do more open, less constrained VMs, this is also done by some companies and by some products. Actually, there is one department in Polygon which is called Polygon Midden, and this is what they are trying to do, a more generalistic VM, also secured with zk. But we want to make it EVM compatible to make it straightforward for a Ethereum developer to move from Ethereum to Polygon zkEVM. Actually, this is also something you ask, I think. Actually, it's very easy for a developer to move from Ethereum to Polygon zkEVM because they can use exactly the same toolkit. They only have to change the RPC URL, and they will move from one chain to another, as you do to any other EVM compatibility chains.
Let me add something.
Yeah, sure.
I think that people is still proving the EVM because of the security model. I mean, it's very difficult to, we have a lot of lessons learned in the EVM, and it's very difficult to create a new virtual machine and then make sure that everything works. I mean, all the experience with the security in the EVM, I think is the thing that makes more difficult to change to another EVM. Despite we know that probably there are better options, but I would say that this is the main reason. And on the standards and everything that we built on top of DVM, but well, the security I think is the main one.
Yes. Ethereum has been Ethereum has been very battle tested, and it's working, so it's safer to just copy.
More questions? This was the last one.
So.
Yep. Okay. Thank you, Ignasi. Well, now we are going to explain. Well, let me first explain a little bit how a transaction goes from the user until the layer 2. Okay, in a high level, and then Ignasi was saying, okay, we're going to see the prover deeply. I would say we're going to see the prover in a very high level because it's extremely complex. So, but we're going to see a little bit how it works inside. Okay, this is the idea. So, well, putting it all together. So, yeah, I can move it. Maybe in the middle, because I'm going to use it quite a lot. Okay. So the user, I'm going to draw. I mean, this is the idea, to use the tablet. Maybe, yes. Yeah, a chair is okay. So I'm going to give a class, I'm a teacher. So, so the user sends the transaction to a node, okay? Well, to a node, and the block that receives the transaction is what we call the JSON RPC, and it's a JSON RPC like the Ethereum one. I mean, it just receives the transaction and checks that things are okay. And then we put this transaction on a pool of transactions to be ordered, okay? It is not ordered, but it's accepted. What Polygon says is, well, what Polygon zkEVM says is, okay, if I accept your transaction, I'm going to process. Eventually, I'm going to process your transaction, okay? If you pay more, I will process it faster, and if you pay less, maybe slower, but it's in my pool. In principle, we don't lose any transaction, okay? So, and then, I mean, all the rollups have chosen this approach. I mean, there is one entity that orders the transaction, and this is the sequencer or the sequencing process. I mean, virtually all the rollups have this process. And, well, what the sequencer does is just order the transaction, and then sends these transactions, sends this transaction to the network so that data is available. Okay, so this is the availability part. Okay, but still there is no, we haven't computed the new state yet. Or the new state is not settled in the network yet. It's only a promise that these transactions will be part of the layer 2 and in this order. Okay, so essentially a sequencer just creates a bunch of transactions and then sends this transaction to the network. Okay, this bunch of transactions is what we call a batch. Okay, well, currently we changed a little bit the name and we call it a blob, but this is more or less the same idea. A bunch of transactions, and inside a batch or currently a blob, we can have many different L2 blocks. Okay, at the beginning we had, because we copied optimism, I think, we had one transaction, one block. Okay, now we have one L2 block, one block of L2 transactions can have one or more transactions. Okay. Okay, so this batch with a lot of L2 blocks, each L block with a lot of transactions or many transactions is sent to the network, and here is where currently we are paying the most of the cost now is because we have to put all this data in the call data of the transaction, so it goes in the transaction, so we have to pay for this. The new AIP, or well, the new schema of dunk sharding and proto-dunk sharding, which is intermediate step, they are going to, allow us to reduce the cost here. Okay, and then this information is stored by a smart contract in layer 1 and say, okay, and we essentially store a cryptographic pointer. We do a hash of all this information, and then, but the smart contract still doesn't know which is the new state. Okay, to move the new state, we need the prover, and the prover will create a proof that proves that we were in a certain state, and after executing these transactions, we are in a new state. Okay, and we submit this proof to the layer 1 smart contract, and the smart contract checks the proof and says, okay, then the new state, consolidated state, and we call it like this, consolidated state. The new consolidated state is this one, okay? And you need the consolidated state because, until the consolidated state is not achieved, then you cannot, send funds or do withdrawals or whatever, okay? But, when the transactions are on the network, you know that eventually the state will happen, but it doesn't happen until the prover submits the proofs, submits the proof to the smart contract, and the smart contract checks the state change, okay? And this is in a high level what Polygon and virtually all the zkEVM approaches do. Scroll, zkSync, and so on. Starnet, well, they do a different thing, I think, but, well, okay. So, yeah, that's it. And, yeah, what we wanted to explain is a little bit, demystify a little bit the prover, because by far is the more complex part and is the more cryptographic and mathematical part, okay? So I know that, here we have audience for different profiles. Let's try to do something that more or less everybody can understand, okay? And so the goal is this, I have a state, I have a batch of transactions, and then I want to prove that if you apply these transactions to the state, you end in this new state. And I'm going to provide, the prover needs to output a proof, okay? We use pi for the proof, okay? So what means creating a proof, okay? Too hard? It's not yet too hard. Okay. So for creating a proof, what we need to do is to create an execution trace, okay? It's nothing else. The execution trace may sound a little bit scary, but it's just a matrix, okay? It's just a matrix of cells, okay? That's it, okay? We need to create the correct execution trace, okay? The correct matrix, okay? So let's put an example, okay? Let's consider that I want to prove this computation here, okay? I want to prove that x0, that a value added with another value and multiplied by 4 And the output of this, you multiply by 2, by x2, well, the result is this one, okay? I want to prove the output of this computation, and this computation has 3 inputs, okay? You cannot see now, but it was x0, it's x1, and x2, okay? Let's wait a little bit. Okay. But the thing is that we are going to prove this computation, but to prove the computation, I have a set of instructions. I cannot do whatever I want. I mean, maybe I could create a single instruction that does this computation, okay? Then I should prove something with one instruction, okay? But let's constrain a little bit this, okay? And let's say that we have only 4 instructions, okay? One instruction that allowed me to copy the inputs to cells in the execution trace. This is one instruction. Another instruction that allows me to add 2 cells, okay, in the matrix. Another instruction that allows me to multiply by 4, nothing else, only by 4, okay? And then another one that allows me to multiply 2 cells of the execution trace, okay? These are my 4 instructions, okay? And I have to do my computation with these 4 instructions. And this is, in fact, what happens with us. I mean, we have a limited set of instructions, and we have to prove the complex computations that are built with this set of instructions, okay? So, and let me assume also that I have an execution trace of only 3 columns, okay? A, B, and C, okay? By the way, we call each column a register also, okay? So column and register, they're going to be, I mean, I'm going to use the same name. I mean, they are interchangeably, okay? Okay, so then how can I prove my computation? By the way, I see that I didn't describe with enough detail the instructions, okay? Let's go. The add instruction, okay? The add instruction, it will add 2 cells in the same row, and then leave the result in a cell in a next row. Okay, this is what add does. Another one, times 4 will take the value of a cell, multiply by 4, and leave the result also in a cell in a next row. Okay, and the multiplication, it will take two cells, and it will leave the result also in a cell in a new row. Okay, this is what these instructions do. So we can do our computation like this. I mean, first we need to make sure that okay, now our machine, our prover, okay, has 3 columns. Okay, I'm constrained to this amount of columns. Okay, to 3 columns. So with my instructions, what I need to be sure is that in A0, okay, in A0 here, I have the first input, okay, x0. In B0, I have the second input, okay, and that's it, okay. I have this thing here is, okay, inputs should be copied in the A0 and B0. The first 2 inputs should be copied in the A0 and B0, so the first values of the column, okay. This is and then here I just add, okay. In this row, I force the add operation. Okay? Remember that the add operation, what it does is to add and then copy the result in the next row. Okay? So this is what we should do. Okay? And then I have the addition here, and then I have the operation times 4. Okay? This is different. I mean, this is also times 4 is multiplying but by a fixed number, which is 4. Okay? So I use the third column, okay, with this number here, okay? And then in this row, I call the times 4 operation, okay? And the times 4 operation multiplies 3 times 4 and leaves the result in the next row, okay? This is the logic of this operation, okay? And then I just copy a new input. I copy the V2, the 5, which is the third input, okay, in B2, which is this cell. I copy the third input, x2, okay? And then I call the multiplication operation. What it does, the multiplication operation, is to take these two cells, multiply, and leave the result in this row, okay? So finally, I mean, this is my execution trace, has this shape, these 3 columns, okay? These several rows, several operations. Obviously, we are going to see how to constrain. I mean, we need also to constrain what these operations do, okay? But if the operations do what they should do, then I will end with the result here, okay? This is the idea. Yep. So we have 2 types of columns here, okay? Or 2 types of registers. A and B, they are registers that you can, I mean, they are what we call witness columns, okay? They will change. If you change the inputs, they will change, okay? So they are computed each time we need to generate a proof. Remember our use case. We are going to receive a bunch of transactions, and we need to prove the new state, okay? So, well, the data of this input, of these transactions will be our inputs that we will put it here, okay? And these columns change, okay, according to inputs. But column C, the column C, for a given computation, it is fixed, okay? So we call these columns the fixed columns, okay? I put it here in gray, okay? They are part of the computation, okay? We're going to do, we will need to do some things with these columns, okay? We have a bunch of values here, but we will need to convert these columns, this bunch of values into a polynomial, okay? So the thing is that these 2, you will need to do a lot of processing per proof, while this thing here can be pre-processed, okay? I mean, given the computation of proving a transaction, or proving a bunch of transactions, your constants columns, you will need to generate them once, and that's it. I mean, then you can prove a lot of batches of transactions without having to rebuild or having to do a lot of computation here, okay? Just creating polynomials and many stuff that we do here, okay? Okay. So in our architecture, the piece, the block that creates, well, maybe block is not a good name, the component that creates the execution matrix is what we call the executor, okay? The executor takes some inputs, it has some rules here, and then produces an execution trace matrix, okay? And this is what we call the executor, okay? I mean, when you have a matrix, you still don't have a proof, okay? We have to do things over this matrix, okay? But the first step is to get a correct matrix, okay? And then we will need to prove that the matrix is correct. There are many projects that decided to create this executor just, you know, I mean, okay, which are the rules, okay? Which are the rules that the matrix need to fulfill? In this case, remember that we were, this row plus this row should be this row and whatever. They code the row, they code all the rules that allow to create the matrix given the inputs. They code this into a piece of software, which is the executor, okay? And then you give the inputs, and it produces the output, okay? And this is programming, I don't know, some language, okay? Rust, for example, okay? This is one option. But the problem, we didn't do it this way, okay? We are doing it. We are doing now, well, we think in doing this now, okay? But the problem is that what we need to do is, we need to prove the processing of several transactions, but the EVM is also evolving, so it's changing. So each time Ethereum changes something, we need to change this code, okay? So auditing the code, written in some language, and so on, this is, in general, difficult, okay? So we decided to create an intermediate language, okay, which is what we call the zkEVM, okay, zk assembly, okay? And, okay. So in our case, we thought, okay, we're going to need to change this executor quite a lot, okay? Because Ethereum evolves, because we're going to make mistakes. I mean, it is going to be difficult to audit this piece of code, that this piece of code exactly processes the transactions that it should, okay? So instead we created an executor that instead of being like, I mean, the other executor could be thought like an ASIC. It's a specific piece of software that generates a specific matrix, okay? But what if instead we thought in the executor as a general purpose processor, okay? It means that it is going to be able to generate different execution traces according to a program. Okay, so now we are going to provide the inputs and also the program. I mean, we are designing this executor to just execute one program. I mean, we don't want to prove different things. We want to prove the execution of Ethereum transactions, okay? But we're going to write it as a program, okay? We call it, I don't know if it's a good name, but we call this program the ROM, okay? Read-only memory, because it's a program, it's just, we are designing just one program. Okay? Maybe we're going to change it because it's not what we finally want, but we are trying to create one program that processes transactions, okay? And the executor is going to read this program. It will see how many columns do we have, which columns are fixed or pre-processed. It will generate all these columns once, okay? And then it will also, with this program, it will be able to read which are the witness columns, and then the executor will be executed each time we want to generate a proof. And will generate these columns that change from one proof to the next, okay? So let me give an example, but it is a little bit, I can do it smaller. Well, let me draw what it is missing here, okay? So here we have two programs, okay? With the same set of instructions that we had, okay? In our set of instructions, we had add times 4 mul, and that's it, okay? But I can build another program, okay? Which is times 4 mul, okay? So this is a different, these are two different programs, okay? The first program is doing this computation, x0 plus x1 times 4 times x2, okay? And with this program, if I give you, these are the inputs, 1, 2, and 5, and then it will produce this execution matrix, okay? And then I can change the inputs and then get another output, okay? But here we have a different thing, okay? Here I have the same instructions, the same rules over the cells, okay? And, but this is another program, another computation. In this case is x0 times 16, then times x1, okay? So how do I do x0 times 16? Well, I don't have times 16, but I have times 4. So I do it times 4 times 4, okay? So I put my input here. For example, I want to compute, and this program, by the way, has only two inputs, x0 and x1, okay? So 2 and 3. So I want to do 2 times 16. Okay, then 2 times 16, but I don't have this operation. What I have is I have a times 4 operation, so I put here a 2 and force this operation over this row. Okay, so it's 2 times 4, 8. Okay, and here in the second row I need to do another times 4 operation. Okay, so 4, 8, 32. Okay, And then what I have to multiply, so I have the mul operation, and then here I have the result. Okay? The idea is that if you have an executor that is able to read these instructions, and it knows, I mean, it has the rule that each instruction needs to fulfill with the cells of the execution trace, then you can build an executor that is general purpose. It will read some instructions, assembly code. We call this the zk assembly. Okay? We will read this assembly, and we will generate an execution trace corresponding to this assembly. And it turns out that auditing, checking, reading, I mean, well, I cannot say that it's pleasant to read assembly, Ignasi, but it's not that bad as reading Rust code, implementing the logic, okay? So it's much better, I assure you, okay? And also auditing and so on is much easier over the assembly than over the program, okay? Our plan anyway is to also, I mean, the problem, well, I'm going to show you the problem of this general purpose executor. The problem is, regarding the general purpose executor, it is much more flexible. I mean, we can change what we prove just changing a little bit the assembly, okay? So it's very flexible. But, well, the problem is that this maybe is a little bit slow, okay? So the idea here is to try to build also a single computation. I mean, we also want to write this executor that just generates the execution trace with a certain program, and that's it, okay? It will be faster, okay, but much more difficult to change. And the idea is to have both and then compare, and we will, I mean, the idea is to check that they both produce the same execution matrix. And then we will be reasonably sure that both are doing the same, okay? But currently what we have is this one, because we are changing quite a lot the proving system until as we approach to the EVM, okay? Adding and adding functionality. So this is the idea. This is the aspect of this assembly code, okay? Here you see step A. Well, I'm not going to, I'm not going to go deep into the assembly, okay? But this is a column that is called step, and what I want to do is to copy the value of in the next row, you will see that the value of A, the column A, is the current value of the step column, okay, for example. And yeah, I mean, if you want to take a look, we have a repo with all the assembly that proves the execution of the Ethereum transactions. You have a highlighter because, assembly is a little bit hard to read, okay? So you can install this extension for Visual Studio Code if you want to check this language, okay? This language is built by Polygon, okay? It's our specific language. Well, we also built a compiler so that it reads the assembly code and then produces a file that can be read by the prover. Okay, well, we have several pieces there if you want to take a look. And this is the idea, okay? We built an executor in which we want to prove just one program, and this program is the read-only memory, or the single program that is the ROM, okay? In fact, Ignasi is what it does, more or less. He works on the ROM, in the team that is writing and testing the ROM, okay? You're lucky not to work with Rust, or work with this thing here. So each time we change the ROM, we are changing, in fact, like the EVM, okay? So in our, we have an identifier of each version of our view of the EVM, okay? And this identifier is the fork ID. If you check our repos, you will see this parameter, fork ID, and this is an exact version of the ROM, okay? When we change the ROM, we need to change the fork ID too, okay? So, yeah, very well, we have a matrix, okay, but how I make sure that the matrix is correct, is doing the computation, okay? It is not enough to provide me a matrix, okay? You should provide me also a list of constraints, okay, over this matrix. In this case, for our computation, remember that it was x0 plus x1 times 4 times x2. So I need these constraints here, okay? I need that A0, this cell here is x0, the first input, B0 should be x1, the second input, and then here I have A1, this value here should be this plus this, okay? So I have this constraint here, and then A2 should be A1 times 4, and so on. I mean, if you provide me a matrix with any inputs that you want, I mean, you can decide this, and these values, which are the inputs, but if you provide me a matrix that fulfills these constraints, this means that you build the computation that you were saying, okay? Well, the thing is that, I mean, these matrices, they will have millions of rows, okay? So I will have like millions of constraints. The thing is that in fact, what we do is not to deal with individual cells, okay? What we do is to deal with columns, okay? Columns and operations. So the thing is that each time, I mean, for the prover, okay, that we create constraints that columns that everybody, but that anybody, any value in the column should fulfill, okay? So this is, I mean, the idea is we have a matrix, okay, and giving constraints per cell will generate a huge amount of, I mean, an extremely big amount of constraints. So what we do is, in fact, constraints with columns. I say A times B should be C, or whatever. Okay? So we create constraints with columns. And each column is transformed into a polynomial. So finally, what we do is create constraints among or between polynomials. Okay? So the first step is to take, I mean, the executor needs to generate these execution trace, reading the assembly, and then we take each column and convert this into a polynomial, and then we say that this execution matrix should, or this set of polynomials, because each column is converted into a polynomial, these polynomials should fulfill this equation here, okay, this identity. And then we have another language, which is the PIL, polynomial identity language, that is a language to describe what these columns must fulfill, okay? So we've built some things, different things, okay? We built we built different languages to prove the batch of transactions, okay? We built the assembly, which is the language that allows the executor to create the correct execution trace, and then we build the PIL, which is the language that allows me to specify exactly what the columns should fulfill, okay? Since, I mean, we are using zero-knowledge technology, in general, in zero-knowledge technology, it turns out that several values are public and others are private. For example, in this case, this is more our approach. Well, this is our approach, okay? So in this case, the 3 inputs, which were 1, 2, and 5 in our computation, and the output, all of them are public, okay? So we call them publics. So inputs and outputs in this example are public. This is our case because we are not focused on privacy. We are focused on, I mean, the thing is that the proof that we are going to generate is small and can be verified in a small time. Okay, so what we're building is a verifiable computation system. Okay, so in our case, anything is, all the inputs are public and the output is also public. Okay, but in general, if you use zero knowledge, you could also prove a computation in which some of the inputs are private. For example, in this case, arbitrarily, I decided that B0 is private. Okay, well, then zero knowledge systems allow you to do this. Okay, to take one of the inputs and make it private. Okay. So, yeah, and these columns here, okay, these columns, they are also, they are also public, okay? They are the fixed values. Okay, so in this execution matrix, I would say that there are two, in this particular execution matrix, I would say that we have 3 inputs, but from these 3 inputs, 1 to 5, only 1 and 5 are public inputs. 2 is a private input. I have an output that is public also, which is 60. And in general, I would say that the publics are 1, 5, and 60, okay? Which are the public inputs and the output, okay? So finally, what it happens is that in our current structure, what we do is, well, after generating the execution trace, well, what happens after, okay? So once we have the matrix, okay, we pass this matrix, and this matrix has constraints because columns must fulfill rules so that the execution trace is correct. Then we have, in this execution matrix, we have witness columns that, remember that they change if we change the input, but it is the same computation. And then we have fixed columns, okay, that contain specific values to do the operations, okay? So they will not change for the computation, okay? So what force that the computation is correct is the constraints and the fixed columns. And then you need to provide me a valid set of witness columns so that it fulfills, all the columns that you provide me should fulfill these constraints, okay? And well, with some magic, this is why I was saying that it is a high-level talk, this one, okay? But with some magic here, the backend generates the proof, okay? And finally, sends this proof together with the publics, okay, to the verifier, which is going to be a smart contract in our case, and the smart contract says, okay, this is correct or this is not correct, okay? As a cryptographic backend today, we are using what is called F-Flonk, and it is around, verify a proof is below 200K gas, which is quite good, okay? And we are using much more technology here because we are using aggregation, recursivity, and many more stuff on the cryptographic part, okay? But finally, we reach this 200K. Yeah, I'm more or less ending. The idea then is that our proving system is like a processor with a set of instructions, okay? Well, the idea is that to prove, what we are doing is to prove opcodes of the Ethereum virtual machine, and to prove each opcode of the Ethereum virtual machine, we may need several instructions in our zkEVM processing system. Okay, so we will need several operations here until we are able to prove one of these EVM opcodes. Okay, because EVM opcodes are quite high level. I mean, each opcode in Ethereum. There are easier one, but some of them are really complex. So we may need a lot of rows in the execution trace to prove maybe one complex operation, okay? And the other thing is that, well, one of the problems that rollups layers 2 have, it was mentioned by Ignasi, is that maybe there is, in the Ethereum virtual machine, there is one opcode that costs certain gas, But for us, maybe it's spending a lot of rows, okay? So is this misalignment between the cost of Ethereum and then the cost for us, okay? So here you can take the solution of just redefining a little bit the gas for you, okay? This is not the approach of Polygon. We think it is better to put like the same prices as in Ethereum, and we are trying that proving each operation, each operation more or less costs the same as in layer 1, or at least they have like the same ratio, okay? If for us, if this costs double in layer 1, then also costs us double, for example, okay? We're trying to align the costs. And then follow exactly the same approach as gas in layer 1. In fact, I'm going to end earlier because you already explained this, okay? So yeah, so this is repeated, but it's the same thing. And yeah, and well, a final comment, okay? And this is just an introduction to the proving system, okay? Very, very high level introduction. The thing is that it is very hard to prove Ethereum transactions in just one matrix, okay? So building just one matrix to prove everything, okay? I haven't explained this in detail, but the thing is that, remember that the relationships should be fulfilled for all the matrix, okay? So how do I, when I'm doing an operation or not doing an operation, how I do this, okay? I have columns, okay? I have columns like operation that is 0. If I'm not doing the operation, I just check 0, okay? And there are a lot of columns that are selecting which operation are we doing, okay? So that the check, since the checks are over all the columns, you have to put what we call selector columns, okay? That select if certain identities should be matched in this row or not, okay? So we have a bunch of selectors. If you have more and more and more operations here in just one single matrix, it starts to grow a lot, okay? So the idea is that we split the computation, in fact, okay? We split the computation in different different other matrices that we call them state machines, okay? So, and then there are cryptographic arguments. There are ways of saying that. Then I do part of the computation in this secondary matrix, okay? I don't need to have all the columns that are in the main matrix. I only have the columns that checking my operation needs. And then I have a cryptographic argument that it is called some lookup, okay? That says that this row here is the same as this row here, and in some way I'm extracting all the proving logic to another matrix, okay? So this is what we do, okay? We call these namespaces, okay? And here in the slides, you have links to the repo, okay? And you can see there our namespaces, okay? We have namespaces to prove ketchups, to prove hash, namespaces or state machines to prove all the memory processing when we write or read to the memory, and so on, okay? We have several secondary matrices, okay? And then the last thing that I want to say is that, okay, finally we have like a main, we have a bunch of matrices, okay? We have the matrix of the main execution, and then we have these other secondary matrices, okay? And currently, these matrices have like a fixed shape, okay? So we have to do a lot of pre-processing, in fact, to see if the batch of transactions fit or does not fit these matrices. For example, if we have a bunch with a lot of ketchups, maybe we are running out of, if this matrix is the one of the ketchups, we want to spend not all the possible, the size is fixed. Okay, so the idea is that first we need to do a lot of pre-executions to see if the transactions can be fit in our structure of matrices. Okay? And this is one of the things that we do many times when the user sends the transaction, we check and say, hey, no, I cannot accept your transaction, but because your single transaction is consuming all my, I don't know, my matrix of Ketchups, for example. Okay? And we give an error that says out of counters. Okay? Out of counters. Right, that's it. But they are zk counters. I mean, it means that we finish with all the resources of one of these matrices. Or maybe the main one, I don't know. Okay? And that's it. I mean, this is the summary of the prover, okay? You just put some private inputs. In our case, we don't have private inputs because anything is public here. We are only using the proof to verify that the computation was well done, but nothing is private. So in our case, we have these public inputs, which are the data of the transactions, then the zk program, and then the executor generates an execution trace, split in two, the witness columns. Well, I mean, we have part of the executor generates the fixed columns. This is only done once. And then each time we generate a proof, we need to run the executor to generate the column, these witness columns. And then we pass the witness columns and the fixed columns and the constraints of these matrices, and the backend with some magic generates polynomial commitments and things like that, generates a proof and generates the inputs. Okay? Well, there's a lot of information. I mean, provers, I mean, they have improved, but to run a proof, you need some resources, okay? And yeah, the verifier just receives the proof, the inputs, and with a relatively small computation says okay or not okay. And this is what the smart contract does, okay? And that's it. That's it, thank you. No, not possible. It was super clear. No, sorry then.
Well, thanks for the talk. So you said you only use public inputs and not private ones.
Yeah.
It's because it's more costly in computation, or for some other reason?
I lied.
Okay.
I must admit. Well, in fact, we use private inputs. Okay. I don't know if you come from the cryptographic background a little bit. Well, in fact, we don't need to use private inputs because nothing is private in our computation. Okay? I mean, transactions, the data of the transactions, which are the inputs, is public and the output is public. We use private inputs. And this is because the verifier, okay? This is a technical detail. It's a very good question, by the way. The verifier is going to check the proof. But to check the proof, you need to pass the publics, okay? If you pass more publics, then the verifier has more work, more gas, okay? So finally, we do a small trick, which is I'm going to pass you only one public, which is the hash of all the publics. So, and we use private inputs. All our inputs, in fact, are private. And as public, I only pass one public, which is the hash of the inputs and the output, and that's it. And then makes the verifier the most, well, it's a trick that is widely used, okay? It makes the verifier very optimal. Yep.
Hi, thanks for the talk. It was very interesting. I have two questions. The first one is, do you have a high-level language that compiles to zkASM, and do you plan to have one? And my second question is, how does it compare to projects that compile high-level languages to like RISC-V instructions and then prove the execution of a RISC-V program? Have you run benchmark to compare to that, for instance?
Okay, let me answer the second one. I think we haven't any benchmark. You're talking about RISC-0 company, right? Or maybe you are from the RISC-0 company, I don't know. we haven't compared, yeah, I don't know. The two questions are related, and I totally agree. I mean, I've been doing pre-audits of the assembly, and it's hard to read, and you know, Yeah, I think the future is to build another language that compiles to the zkAssembly or use any solution of any of these companies right now. I think I think we haven't done this yet, but I think is the way to go. So I agree with you. We haven't done and we have not compared, okay? But yeah, that's it. Yeah. Well, another feature that we are developing, okay? Just to, well, no, it was bad cops, but well, let me see the questions and maybe I will tell you the last thing that we are developing.
Right, so he asked one of the things that I wanted to ask. I also wanted to ask, since you talked about developing a ROM that compares to the EVM, it reminds me about how we need client diversity on Ethereum. Like we have Get and we have other clients. Do you also need to, or is it convenient to have different ROMs that in the end prove the same computation so that you have some sort of diversity and, you know, like redundancy?
Mm-hmm. This is the idea of the single computation executor, to have at least two, and if the two generate exactly the same matrix, we are quite sure that we are doing the things okay according to some specification. So, but we also check when we do the computation, and if not, Ignasi can correct me, we also check that the resulting state, we took the JavaScript implementation of the EVM, right? And then we check that the ROM and the JavaScript implementation do the same. And we use the Ethereum test vectors to see that everything is matching. Okay, so yeah, we do these checks. Definitely having another executor is another layer of, being sure that we are doing the things right. Mm-hmm.
Yep.
That's it? Ah, sorry.
No. So I have a question with these matrices. So I understood that basically when you take a program, you take the trace, but for instance, if you have a loop or you have a recursive function, then the traces are getting super big, right? Or, when, because I understand that that thing can grow super big. I mean, if you take a execution that consumes a lot of gas, then your matrices can be super huge, right? And then the second question would be like, how are the machines for these resources? I mean, do you use like, supercomputers for that? And
we use big computers. Yesterday I was seeing the guy from zkSync, and they say that they can run the prover in a laptop, something like that. I don't know how they do it. In fact, we use servers that are mainly we need processing and a lot of memory, because you have to. These matrices are big, yeah, and we have to move all this data. So,
yeah, super
and to parallelize things also. Yeah. So, but regarding the jumps. Having jumps is not, ifs in the code and so on, or fors or whatever, or branches in our code in general, is not so hard because, I explain you in a very, very high level, okay? But we need to implement the EVM who may have ifs, fors, and so on. We have also a program counter that is seeing which line are we executing, and then we have jumps, okay, and then we code all the constraints to force that the jump is well done and you're jumping to the correct position and so on. So, they are big matrices, but we can execute quite a lot of transactions in one of these matrices. Okay, the matrices they are around 2 to the 22, 2 to the 23, something like that. Okay.
Okay. And another question is with the verifier. What happens if the verifier says like this proof is not correct? That you are stopping the machine? How are you recovering from that?
Really, really good question. And also we had some problems. What we use is what we call the proof anything paradigm. The prover, you give me, speaking badly, give me any shit that you want. I'm going to prove that. I'm going to prove this. I'm going to prove you what this data does. If you give me something that it has not the correct format, I don't know, they are not transactions, they are not encoded with our IRLP or whatever, the proof is the state is the same, and that's it. Okay, so we always prove anything. We are able to generate a proof that says that the state is not changing because what you provide me cannot be decoded, for example. So yeah, it's very important. And this is also a security issue that from time to time we forget, and it has bad.
Yeah, because it can happen that
bad results. Yeah, if you forget some of these things, then someone is going to build a transaction that it will send to the network and explode our system, because then we cannot prove that we must prove that this transaction does whatever. Nothing, but we must prove it. It cannot break the prover. Okay.
Last question.
Round of applause, please.
Thank you.